Welcome to week 4. We'll move on to our next topic, the p-adic numbers. This is week 4 and lecture 17 now. The topic of this lecture will be the p-adic absolute value. Our goal eventually is to describe the p-adic numbers and the p-adic integers, for which we'll need the p-adic absolute value. So recall, if you have a prime number p, we had this valuation ring that we got by localizing z with respect to the prime ideal p. This is a valuation ring inside Q. And correspondingly, we had this valuation function. So let's try to write this down explicitly. The corresponding valuation on Q cross is defined as follows. So how do we do it? So if you have an element in this valuation ring, then you write this as a fraction with the numerator in z and the denominator is in z but not in the ideal generated by p. So another way of saying that is that y is co-prime to p. And now furthermore, you look at the numerator and collect all the powers of p . So you write this as p to the n alpha times z, with z being co-prime to p. And so on, thus, if alpha, since z localized at p is a valuation ring, if alpha in Q cross belongs to z localized at p, then you define the valuation function as this n alpha, which belongs to z. And if alpha in Q cross does not belong to z localized at p, then alpha inverse belongs to z localized at p, since it's a valuation ring. And define valuation of alpha in that case to be the valuation of alpha inverse, but with a negative sign. Okay, so in short, we have a function from Q cross to z. Sort of picks out how many times p divides that rational number. And this function lets us define an absolute value on the rationals, and it's very similar to the Archimedean absolute value. It's similar to this usual Archimedean absolute value. It's both similar and different, but its definition is the following. So if you give me a rational number, if that rational number turns out to be 0, I'll just define the absolute value to be 0. And if alpha is not 0, then I look at this function 1 over p raised to this exponent given by the valuation. Okay. Now I have this base as 1 over p, and this is just for convenience. So we simply choose the base to equal 1 over p, just to emphasize the choice of the prime. actually we could have chosen any number that's any positive number that's less than 1. Okay, and so we have this function, this p-adic absolute value from Q to the positive rationals, but I'll just to emphasize the similarity with the usual Archimedean value, I'll write that it takes values in the non-negative real numbers, and it satisfies the following standard properties. So one is that, so when would this p-adic absolute value be 0? Well, you can see that if alpha is not 0, then this expression 1 over p raised to this exponent, where this exponent belongs to the integers, that's never 0. So the p-adic absolute value is 0 precisely when alpha equals 0. So the p-adic absolute value is 0 if and only if alpha equals 0. And it's also not hard to see that it's multiplicative. This uses the fact that the valuation is additive, and it satisfies what's sometimes also called the ultrametric property. It is less than equal to the maximum of the p-adic absolute value of alpha and the p-adic absolute value of beta. And just as I said earlier, properties 1 and 2 are easy to check. Property 3 is also easy to check, but let's just verify it. To verify property 3, observe that if alpha is 0 or beta is 0 or alpha beta is 0, alpha plus beta is 0, then property 3 is straightforward to verify. So let's just assume that alpha is not 0, beta is not 0, and alpha plus beta is not 0. And you have these two numbers, alpha and beta, and just suppose for simplicity that the p-adic valuation of alpha is larger than or equal to the p-adic valuation of beta. What does that mean? That is, the minimum of the two valuations is actually the p-adic valuation of beta. But you have that the p-adic valuation of alpha is larger than or equal to the p-adic valuation of beta. If you raise it to the pth power, you get that p raised to the p-adic valuation of alpha is larger than or equal to p raised to the p-adic valuation of beta. And then if you take reciprocals, then the inequality sign switches. So you have 1 over p raised to the p-adic valuation of alpha is less than or equal to 1 over p raised to the p-adic valuation of beta. And this just means that the p-adic absolute value of alpha is less than or equal to the p-adic absolute value of beta. And this just means that if you look at the p-adic absolute value of alpha and beta, the maximum of that given by this inequality, the maximum is just given by the p-adic absolute value of beta. Okay, so so we have this one relation involving the p-adic valuation and one relation involving the p-adic absolute value. So if you just compare them, so if you use the property of valuations, you have that the p-adic valuation of the sum is larger than or equal to the minimum of the p-adic valuation of alpha and the p-adic valuation of beta. But by assumption, the minimum is given by the p-adic valuation of beta. And again, if you just take p powers, you get the p-adic p raised to the p-adic valuation of alpha plus beta is larger than or equal to p raised to the p-adic valuation of beta. And once again, if you take reciprocals, you get that 1 over p raised to the p-adic valuation of alpha plus beta. The inequality sign flips since you're taking reciprocals. You're using the fact that p is larger than 1 and 1 over p is strictly less than 1. And so this means that the p-adic absolute value of alpha plus beta is less than or equal to the p-adic absolute value of beta, which was the maximum of the p-adic absolute values of alpha and beta. And so this verifies property 3. And another observation is that so property 3 actually implies the usual triangle inequality. So if you have the absolute value of alpha plus beta, property 3 tells us that it's less than or equal to the maximum of the p-adic absolute value of alpha and the p-adic absolute value of beta. But both of these numbers are non-negative. So the maximum could be either the p-adic absolute value of alpha or the p-adic absolute value of beta. Let's say it's the p-adic absolute value of beta. Now you can always add any positive number to it and that will still be an upper bound. So let's just add the p-adic absolute value of alpha to it. Okay, so this just so the absolute value of the p-adic absolute value of alpha plus the p-adic absolute value of beta, that's always larger than or equal to the maximum of the p-adic absolute value of alpha and the p-adic absolute value of beta. So that's enough to deduce this triangle inequality. Okay, so this is the triangle inequality. And we also get an induced function from this p-adic absolute value. That's the usual metric function, which is dp from q cross q, again to the non-negative real numbers, where if you have alpha comma beta, the distance between them in some sense is you take the difference and compute the p-adic absolute value. And once again, it's not hard to see that this function dp defines a metric. We'll call it the p-adic metric on Q. And the proof is just, you just have to verify the metric properties. If you have the same point, the distance between alpha and alpha, the same point is just, you take the difference and compute the p-adic absolute value. That's just the p-adic value, absolute value of 0, which by definition is 0. And then you need to check positivity. So if alpha is not equal to beta, then you want to compute the distance between alpha and beta, which is the p-adic absolute value of the difference. But if alpha is not equal to beta, alpha minus beta is not 0. So the p-adic absolute value of alpha minus beta cannot be 0. And the next thing that you want to check is symmetry. And just a small observation is that if you have beta minus alpha, that's just minus 1 times alpha minus beta. So if you take the p-adic valuation of beta minus alpha, that's just the p-adic valuation of minus 1 plus the p-adic valuation of alpha minus beta. But we know that, so we've seen that the p-adic valuation of -1 is in fact 0. So the p-adic valuation of beta minus alpha coincides with the p-adic valuation of alpha minus beta. So this fact that the p-adic valuation of -1 is 0, so this was seen in lemma 23, this was in lecture 9. Okay, and so thus it's not hard to see that if you take the difference beta minus alpha, that's the same as the p-adic absolute value of beta minus alpha is the same as the p-adic absolute value of alpha minus beta, because on the one hand the left hand side equals 1 over p raised to the p-adic valuation of beta minus alpha, but the right hand side is 1 over p raised to the p-adic valuation of alpha minus beta. But we just saw that the exponents are the same, so these quantities must equal each other, and so the left hand side, the right hand side is the distance between alpha and beta, and the left hand side is the distance between beta and alpha. Okay, so this is property 3, which is called symmetry. And property 4, which was this property of triangle inequality, which is also something that we just saw. So if you have distance between alpha and say a third point gamma, you want that to be less than or equal to the distance between alpha comma beta plus the distance between beta and gamma. And again, just unwinding definitions, the left hand side is nothing but you take the difference between alpha and gamma and compute the p-adic absolute value, and then you do this trick of adding and subtracting beta, and then using the triangle inequality for the p-adic absolute value. That we just observed earlier, you get it's less than or equal to the difference of the p-adic absolute value of alpha minus beta and the p-adic absolute value of beta minus gamma. And the distance between alpha and beta, that's nothing but the p-adic absolute value of alpha minus beta, and the p-adic absolute value of beta minus gamma is nothing but the distance between beta and gamma. So this gives us the triangle inequality, and thus dp defines a metric on Q, and this completes the proof of the proposition. And what's also true is that once you have a metric on Q, you have an induced product metric and a product, and hence a product metric topology. On finite many copies of Q, so in particular Q cross Q. And again, just some facts from topology. So in fact, you can give many different metrics. That one can impose on Q cross Q from the metric on Q. But the sort of connecting property amongst all these metrics is that they define the same topology. So you could have different metrics, but they all give rise to the same product topology. On Q cross Q. So we have many different choices of metrics, and just for simplicity, we'll choose the supremum of the coordinate-wise product metric. So if you have, say, alpha comma beta 1 in Q cross Q, and alpha 2 comma beta 2 also in Q cross Q, I will call the distance function on Q cross Q also by the same symbol dp. So if I want to find the distance between alpha 1 beta 1 and alpha 2 beta 2, I take the coordinate-wise distance. So alpha 1 minus alpha 2 and its p-adic absolute value, that's in the first coordinate, beta 1 minus beta 2 and take its p-adic absolute value, that's in the second coordinate, and I just want to take the supremum or maximum of them. Okay, so this is a metric that gives us this metric topology on Q cross Q. And again, some more facts from topology. So in a metric space, continuity is the same as sequential continuity. So suppose you have a map, say x to y, and it's a map between metric spaces. So it turns out that f is continuous if and only if f takes convergent sequences. So suppose you have a convergent sequence, let's say xn, and what does it mean for it to be convergent? That this limit exists and it's some x naught. So f takes convergent sequences in x to convergent sequence in y. So if you give me a convergent sequence, then it's enough to check that the limit n goes to infinity of f of xn exists in y. Okay. So in other words, if you have a map between metric spaces, it's enough to prove sequential continuity to deduce that the map is continuous. Okay. And so what do we want to show? So we want to show, okay, so we have this addition function, you have this multiplication function, and you also have the inversion function. So if you have alpha comma beta, that goes to alpha plus beta. You have alpha comma beta, that goes to alpha beta. And you have q and q cross, where you send alpha to alpha inverse. So again, you put impose the subspace topology on Q cross. And so we have these three maps, and what we want to do is we want to show that these maps are continuous. So we want to show that these maps are continuous with respect to the topologies induced by this p-adic absolute value. Okay, and by the above fact, it's enough to show that under these maps, convergent sequences go to convergent sequences. Okay, And in fact, what we'll show is that addition and multiplication take Cauchy sequences or send Cauchy sequences to Cauchy sequences. Okay, so we'll see the proof of these facts in the next lecture. Thank you.